Welcome to the recording of section 6.6, part C. Here I have the graph of cosine. We can see that these are the points where cosine is 0. So you can see that here I have -1 times pi over 2, 1 times pi over 2, 3 times pi over 2, 5 times pi over 2, and so on. So in fact, cosine of x is 0 if and only if x is equal to pi over 2 times k for some odd integer k. Now I'm interested in studying the function tangent. Tangent of x is equal to sine of x over cosine of x. Because here we have cosine of x in the denominator, tangent of x has domain all numbers x whenever cosine of x is not 0. That is all numbers except for pi over 2 times k, where k is an odd integer. And the reason I can have all numbers is because the domain of sine of x is all numbers. So as you can see here, tangent is not a one-to-one function. It does not pass the horizontal line test. So we restrict the domain of tangent. The most natural choice is between -pi over 2 and pi over 2. So this is the restriction that we will choose. Now, tangent is a one-to-one function, so we can define its inverse function. The notation for the inverse function of tangent is arctangent. Another notation that is often used is tan to the -1 of x, but this can be confusing. So these two are not the same. The right one is saying 1 over tangent of x, but the left one is the inverse of tangent. So arctangent of x is not the same as 1 over tangent of x. So the restricted tangent, like I said in the previous slide, the domain is the open interval between pi over 2 and -pi over 2. The image is all numbers. Right? This can go on forever. And the domain and image of the inverse function arctangent is switch. So the domain is the set of all numbers. The image is the interval between pi over 2 and -pi over 2, but not including the two endpoints. Now I'm going to compute the derivative of arctangent of x. So first, I write arctangent of x as y. And I want to work with tangent instead of arctangent. So I write tangent of y, and then tangent of arctangent of x. But tangent and arctangent are inverse functions. So this is x. So now what I have is I have this situation where tangent of y is equal to x. This means that I can draw this point here, and I can think of this x as x over 1, where x is the vertical part and 1 is the horizontal part. And that's why I have drawn here 1 as the horizontal part and x as the vertical part. And here, this is the case where x is negative or 0. And so my point is over here in the 4th quadrant. And I can also have a situation where my x is positive or 0. And so my point would be in the 1st quadrant. So in the first case, my angle y is in between negative pi over 2 and 0. Because if you look at the graph, when x is negative or 0, the value is between 0 and negative pi over 2. And in the second situation, the angle y is going to be between 0 and pi over 2. Because when you look at the graph, when x is positive or 0, the value of arctangent is between 0 and pi over 2. So this point is in the 1st quadrant. And the case 1 is in the 4th quadrant. So we did step 1 already. And the next, and we drew a triangle in step 2. In step 3, we'll do implicit differentiation. So I take the derivative with respect to x on both sides. So on the right-hand side, it is just 1. On the left-hand side, I have secant y squared. And because of chain rule, I do dy dx. And I'm interested in dy dx. So I have 1 over secant y squared. And 1 over secant is cosine. So this is cosine y squared. So we're almost done, except this is in terms of y, but I want something in terms of x. So now going back to the picture we drew earlier, here I have that the horizontal part over the distance from the origin to the point, or you can think of it as the hypotenuse length, that will be cosine of the angle y. And looking at this picture, the horizontal value is 1. And the distance from the origin to the point, or the hypotenuse length, is square root of 1 plus x squared. And this is true for both case 1 and case 2. So cosine y is this value. So cosine y squared is just this value squared. So I have 1 over 1 plus x squared. And now I know how to compute my dy dx, because dy dx is cosine y squared. So it's just 1 over 1 plus x squared. So the derivative of arctangent is 1 over 1 plus x squared. In the previous slides, I was drawing 2 different cases, but in fact, the domain in the book has been chosen so that when you do computation, it's enough to just draw the case where the point is in the 1st quadrant, and your computation will work out. So you can just draw this type of picture where the shape of the triangle looks like this, and this is your angle. And this is basically the same as saying that this point is in the 1st quadrant. Now let's apply what we just learned to solving an integral. Now let's try u substitution. So try different values of u that may work. So pick some values that come from the integrand. So if u is sine of x, then du would be cosine x dx. But that doesn't look very helpful because then I'll still have this 1 plus cosine x squared. So let me try u being cosine x. Then du would be negative sine x dx. So that seems better. So let me try this. Then I have, because 1 over 1 plus cosine x squared would then be 1 over 1 plus u squared. So this looks like the expression in the previous slide. And also this value, negative 8 sine of x, would be equal to negative 8 du in this substitution. So this is good. So this is one substitution that works. So let me do that. So now I have 1 over 1 plus u squared times negative 8 du. And let's just double check that there are no x. Everything is in terms of u. So that's good. If you have anything in terms of x, then you haven't done the u substitution correctly. Now, in the previous slide, we saw this. So that means that the integral of 1 over 1 plus u squared du is arctangent u plus c. So let's apply that. So now I have negative 8 times arctangent of u plus c. And now I just have to replace u with cosine of x. And here are some exercises where you can apply a similar technique. The last two functions that I want to talk about are secant x and its inverse. So let's look at some properties of the secant function. Recall that secant is 1 over cosine. So if we draw this circle with radius r, you can think of cosine of theta as being x over the length of r. So 1 over cosine is r over x, assuming cosine theta is not 0. So the domain of secant is all numbers as long as cosine of that number is not 0. So I have the domain is all numbers for which cosine theta is not 0. In other words, all numbers except the number k times pi over 2, where k is an odd integer. So next, let's look at what is the image of secant. Let's reason this out. So the distance from the origin to the point, like if you look at this picture, this distance is always going to be bigger than or equal to the distance, the horizontal distance from the origin to this x value. So then I have r over x is always bigger or equal to 1 if x is positive, and r over x is smaller or equal to -1 if x is negative. This means that secant theta is bigger or equal to 1 or smaller or equal to -1. Now also notice that cosine can be as close to 0 as we want just from looking at the graph of cosine. So that means that secant, which is 1 over cosine, so it's 1 over a value that we can make as close to 0 as we want, we can make it as big and either positive or negative as we want. And so the image of secant can be as big and negative as we want and can also be as big and positive as we want, but it's also bounded by these two values, 1 and -1. So this is the image of secant. So all numbers smaller or equal to 1 or equal to -1 or bigger or equal to 1. In order to define the inverse function of secant, we first need to restrict the domain so that secant becomes a one-to-one function. The choice of domain that is used in the book is the union of the interval from 0 to pi over 2. So let me draw that in the graph. 0 to pi over 2, but not including pi over 2. So this is in the first quadrant. And then the other interval is from pi to 3 pi over 2, but not including 3 pi over 2. So this is in the third quadrant. Now, this is not the only natural choice. Another natural choice that might look more natural to you right now is the union of the interval from 0 to pi over 2 and pi over 2 to pi. So that would be like taking this part. So taking the whole interval, except we have to remove pi over 2 because secant is not defined at pi over 2 because cosine is not defined there, or because cosine is 0 at pi over 2. But so in some situations, there are people who do use this choice, but the reason our book doesn't use this, and the reason we're also not using this in this class, is because if we were to use this choice, the derivative of the inverse function would be more complicated. So we're choosing this other one because then the derivative would be simpler. So this is the one we have. So 0 to pi over 2 and pi to 3 pi over 2. Now we have a one-to-one function, and the range of this new secant is the same as the usual secant. So all numbers smaller than or equal to -1 or bigger than or equal to 1. Let me write down the same information more compactly. So the restricted domain of secant that we will work with in this class is all numbers in the interval 0 to pi over 2, but not including pi over 2. And the interval from pi to 3 pi over 2, but not including 3 pi over 2. So in the graph, it's these numbers. The image, so the numbers can be as big as you want, but it has to be smaller than or equal to -1, or bigger than or equal to 1. So we denote the inverse function by arc secant, and sometimes you might see this notation, which I will try not to use, because you might think that this means 1 over secant x, but it's not. So then we flip the domain and image of the original function. So now the domain of arc secant is just the image of secant. So all of the numbers smaller than or equal to -1, and also the numbers that are bigger than or equal to 1. And the image of arc secant is from 0 to pi over 2 and pi to 3 pi over 2. And let me label that in the graph. So I have from 0 to pi over 2, and also from pi to 3 pi over 2. So when x is in the interval from -∞ to -1, we can see that arc secant is in between pi and 3 pi over 2. So it's like this part here. And when x is in the interval from 1 to infinity, we can see from the graph that arc secant is in the interval from pi to 3 pi over 2. So if we had chosen a different restricted domain, then the graph of our arc secant would look slightly different.